Mano, do you know what deja vu means?
The same event occurring on the same condition.
It's something nostalgic that reminds you of something that you have had experienced before.
Same event occurring on the same condition.
Not necessarily, it's a psychological feeling.
Same thing, like necessary.
So, there are a lot of foreign students here. I hope you know what this means. What a foreign student. Titus, do you know what all this means? No? You know what duck soup is? No? What is that? No, I don't ask you to say in Cantonese because duck soup has no meaning in Cantonese. Not Kong, but that does that mean anything?
Was that all?
I just gave back a new homework.
Was that all of it?
There was what was given to me in the box. Okay, I just went to the
Oh, there's another file here.
took out.
Oh, no,
Those were the old ones.
That's homework 8 though.
There's another file coming up.
Okay. So let's see what we can do today. Okay, so these are the slangs you have to learn today. So, I like to do a very simple convolution example that you have two square functions. Say one is of duration A. Okay, this is bracket. So let's call it just f A of t. And then the other one is just, the textbook likes to call it h of t. Why don't I just call it f of t and h of t then, when they convolve two functions. Okay? So when you convolve these two things, you get an output usually called y of t in the textbook. And order does not matter. When order does not matter, there's also a mathematical name for it. What is that called in mathematics? What? Associative is not. Associative means that grouping does not commutative. Okay? So this is called the commutative property. Okay, associative is when AB times C is to the A times BC. This is associative in mathematics. Okay, but when order does not matter, that is called commutative. So let's convolve these two. It doesn't matter which one we pick to be the first one or the second one. And what you do first is that when you convolve, then you can write down an equation as such, which is d tau, f of tau, h of t minus tau. Okay. So what you do then is to find h of minus tau, and then you shift it by t. Okay, so these are the two processes that you have to do to the second function. The first function remains unchanged. So if you apply h of minus tau to this function, what do you do essentially? You flip it around. You flip it around. So the first action is that if I were to plot this as a function of tau, h of minus tau will look something like that. Minus b, 1. Okay, that's the first thing that happens. The second thing that happens is that you shift it by t. H of t minus tau is the same as, instead of when the origin corresponds to tau is equal to 0, the origin corresponds to tau equals t. Okay, I'm still plotting this as a function of tau. So this will be something like minus b plus t. Okay, can you see that when I shift that function over? Yes?
Won't it matter if like t is positive or negative which way they shift it? Will we know if t is positive or negative?
T is 0. T is a number on the left-hand side. So this t is a running value that can go from t from minus infinity to infinity. So t runs over all these possible values when you compute this integral. Okay, you keep changing t in order to get a new value on the left-hand side. So if t is equal to 0, you have this picture over here, and this is an arbitrary value of t that I have. Okay? So the next thing you do is to multiply this with that picture over there and integrate. And find the overlap. So when you multiply, you do the overlap integral. Okay? So if you have f of tau now multiplied by h of t minus tau, okay, it will look something like this. You can see that the overlap only, and then the other one is just like that. A, and then this is B. T, tau equals T. Okay? And then this one is tau equal to 0, and this one is tau equal to P minus B. Okay, so the overlap part is this part over here. Okay, the overlap part is that part over there. What is the overlap when t equals 0? When t equals 0, the overlap is 0. So if I were to compute this integral, y of t as a function of t now, when t is equal to 0, there should be nothing on this output. Right, because the overlap is 0. Okay? So there's nothing before t less than 0. T less than 0, there's no overlap at all. Can you see these two pictures? When t is less than 0, they don't overlap at all. And then when t is equal to 0, they start to touch each other. But there's no overlap area. The area under the overlap is still 0. But then as you move the thing to the right, t starts to become larger than 0. There will be an overlap. The area becomes larger and larger. And how does the area increase as a function of t? It increases linearly. Very good. Increases linearly. Okay? Increases linearly. And it will reach a maximum. When would the overlap integral reach a maximum? It reaches a maximum when t is equal to a, right? It reaches a maximum when t equal to a. Okay, when t equals to a, what is the area that is in overlap? It's just 1 times a, right? So this maximum value is just a. Okay, that would be the overlap integral when t reaches a. And then when t exceeds that value, what happens to y? What happens to the overlap integral? If t is larger than a, not 0, if t is larger than a, what happens to the overlap integral? Not yet.
It'll stay.
It remains constant for a while. Very good. It remains constant. Okay. So if I draw a picture, then if I have a over here, for the first picture over there, and then if t is larger than a, I have this second thing coming this way. Okay. Tau equals t, and this is tau. And this is t larger than a case. This is tau is t minus b case. When t is larger than a, this is the picture I should have of this thing. Okay, this is the picture I have, and the overlap integral essentially remains constant for a while. How long does it remain constant? Until t equals what? Until this part here becomes 0. Okay, this thing moves over so much that this part becomes 0. Okay? So it would be t equals b. Okay? And then when t equals b, this part becomes 0. And what happens to the overlap integral? Yes?
When you say overlap integral, do you mean just like the physical overlap of the two areas, or the integral of their
overlap of the two areas and then integrating the overlap part? That's what I mean by overlap integral.
But you don't
Overlap
multiply.
integration maybe should be the proper word.
But you don't multiply the signals.
I do because for this case it's very simple. Both of them are 1.
Oh, so if they're more complicated,
If they are more complicated, you have to multiply them. I'm doing the simplest example possible. Okay, I'm doing the simplest example possible. And then you just have 1 times 1, always. Okay? So this is always 1. This is always 1. And this is also 1. So after that, it will decrease monotonically. Okay? Until when? When would this leave this thing? A plus B, right? A plus B is when the overlap ceases to exist again and everything would be 0. So this is how you can find the solution graphically. Okay? Another fact that you should know about convolution is that irrespective of the shape, this thing can be complicated in shape, this can be complicated in shape. If the duration of this is A, and the duration of the second one is B, the duration of Y is always A plus B. Okay, duration of Y is always equal to A plus B. Can you see this pictorially? It doesn't matter what the shape should be. For f of t, what the shape of h of t should be. If one is the duration of A, the other one is the duration of B, after convolving them pictorially, the duration is always A plus B. Okay? What happens if, say, the second function, h of t, is in time delay? H of t looks something like this. T naught plus B. This is 1. What happens if I just time delay h of t by t naught, yes?
It will shift over Y.
Everything will be shifted a little bit to the right by t naught. And that we learn as one of the properties of convolution, right? And remember that we have this property that if y of t is f of t convolving with h of t, then y of t minus t naught is just a time delay version of this convolving with that. It can be either one, okay? It doesn't matter which one you pick. Convolution is not biased, okay? And it works on either one of them. And so when you have one of them delayed, one of these functions delayed, the output will be delayed by the same amount. And you can see this pictorially, can't you? You can see this pictorially by flipping this around, and then this will be moved slightly to the left, and then you have to move this quite a bit to the right before an overlap integral exists. And then you pick up the overlap integration, and then it will be delayed by a little bit, and then it goes to 0 later. Okay? So this thing is something that you should know. This is very important. One of the properties of convolution. Are there any questions regarding this? Okay? Duck soup, right?
Ah, you're stuck.
So, another property that I like to mention is that we learned that if ft convolves with h of t, then its Fourier transform is f of omega times h of omega. Okay? But if you have this in reverse, things also work. If you multiply two functions, then its Fourier transform is 1 over 2 pi f of omega convolving with h of omega. Okay, I don't have to prove this because I already proved the first one. The proof is very similar. You just plug in Fourier transforms and substitute them and exchange order of integrations, you can get the second proof. Okay, it's another thing that you should know. Okay? So let's go to section 9.1.3 if you don't have any more questions. Okay? Section 9.1.3 9.1.3 is full of examples. Example 9.5, for instance, asks you to work out the convolution of a unit step function with an exponential function. So I presume you know how to do that. I don't have to go through it. It's a plug and chuck exercise. Okay? You use the convolution formula, plug in u of t here, and then e of t here, and then time delay it appropriately, and then set the limit of integrations properly, and you get the answer. I'm not going to do that, okay? Exercise 9.5. Exercise, or example 9.6. You're given that h of t is equal to e to the minus t u of t. F of t is equal to e to the minus 2t u of t. Then you're asked to find y of t is equal to h of t convolving with f of t. Okay, so the first function looks something like that. That's a function of t with the value of 1 here. The second function also looks similar, but starting out with 1 but decays twice as fast. Okay, you're asked to find the third value. You can flip it around, find the overlap integral, perform the integration, and get the answer. Unless you want me to do it, I wouldn't do it. It's too mundane, I think. All of you know how to do this, right? Unless you want me to do it, I wouldn't do it. Okay?
Laura still sees problems for breakfast. Sits down and does it.
Or you can do it at breakfast by yourself. Okay? Okay, exercise 9.7, or example 9.7, is very similar to example 9.6. Example 9.6 asks you to find the convolution value for only one value of t. Example 9.7 asks you to find it for all time. Okay, so it's also duck soup. Okay, if you know how to find it for one value of t, you know how to find it for all values of t. Okay. So let's try to do this graphically then. You know how to do it mathematically by plug and chuck exercise. So let's try to do this graphically and see what the answer should be if we were to do this convolution graphically. So you flip one of this around. You flip h of minus tau as a function of tau, you get something that behaves like that. Okay? And then you time shift it. T minus tau, so it looks something like this. Tau equals t. Okay? And then you multiply by your f of t and integrate. So if you multiply by f of t, then the overlap integral will look something like this. So you have one function that looks something like that. The other one just looks something like that. Okay, so this is f of tau times h of t minus tau. So it looks something like that, and the overlap integral is actually this function here multiplied by this function here. So you have to figure out the product. You cannot just take this value or that value and multiply them together to get the true value. Okay, that answers a question mark that you cannot assume them to be always 1. Okay, now you have to take the two functions and multiply their values together. Okay, so you can do the multiplication mathematically. It's just you can also do the multiplication this way. On paper, if you want to integrate, but let's intuitively find out what the answer should be and how it should look like. Okay? So this is tau equals t. So if I were to look at y of t now, when t is less than 0, what happens to the output y of t? When t is less than 0? Nothing. I get nothing because there's no overlap. If t is less than 0, there's no overlap between these two, this function and that function over there. Okay? So this is f of tau. This one is h of t minus tau. There's no overlap. Okay, so it's 0. And then when t is starting to be larger than 0, it starts to pick up a value. Does it pick up a value suddenly or gradually? Okay, so let's assume that when t is equal to 0, there's no overlap at all. So the value should be 0. But if there's an infinitesimal t is slightly larger than 0, how big would the overlap integral? And how big would the overlap area be? It will be still very small, right? So if the overlap is very small, if I were to draw it correctly, the overlap looks something like this. Okay? So the area underneath will be the product of these two functions and then calculating the overlap integral under the thing. And this is t is very small. T is delta. How big is that area? The area is about the size of delta times the height, right? The height is approximately equal to 1 in the top of the area there. So you would expect that the area is roughly delta. Delta is a small number. Okay? Agree? So the answer is roughly proportional to delta, where delta is the small t values that you start to push this over, and it's a very small overlap region. So you would expect that this thing would increase linearly with time. Agree? It increases linearly with time. Because that overlap integral, the area under which you're trying to compute, is roughly proportional to the overlap time times the height. The height is roughly 1. Right? Both of the functions are 1, right? This function is 1 over here. Okay, so approximately in the vicinity of the peak, this value is approximately equal to 1. Okay? So the integral should increase linearly with time. Everybody agrees on this, or is it difficult to envision? I see a lot of glazed eyes, so it must be a very difficult concept. Nancy, what do you think? Do you accept this? What is that? Oh, because delta is my time. My t is equal to my delta. I'm setting t to be very small. This is the general picture for arbitrary value of t. Okay, let me start with t is equal to 0. There was no overlap, so the integral is 0. But let me set t to be a very small number. So t is a small number delta. Delta is usually used to represent small quantities in mathematics. Okay, so if I ask you to approximate the integral that is in the overlap region, isn't the integral roughly delta times the height? The height of both of the functions are about 1, and we multiply them together. They are not exactly 1, but about 1. Okay, just about 1, right? So Liu Qing got it. So it's about 1, right? So then that integral is proportional to t. Okay? Proportional to t, and then hence this thing should increase linearly with t. Until when you proceed further, then this argument that I have is not valid anymore. Okay? And it turns out that if you do the math correctly, it has to come down. What happens is that as things start to increase for a while, okay, but then it will have to come down. What goes up must come down. Okay? What goes up must come down. Why does it come down? Well, if you look at the two picture, as you have very large overlap, this function would have moved all the way to the right, and then this function is still there, stationary, not moving. This is my f of tau. This is my h of t minus tau. You can see that the overlap integral is very small. These are small values. Okay, small values times large value, the small values dominate. This is also dominated by the small values. So when you have small values times large value, the answer is small. Okay, so the area underneath the overlap integral becomes smaller and smaller. So whatever goes up must come down. Okay? If you're not believing in this answer, of course you multiply these two things up, go through the exercise of multiplying them out rigorously, and then integrate term by term. You plot out the thing using a computer program to get the same answer, more or less. Okay? Is this okay? Or you want me to repeat this? No, right? Not necessarily to repeat this because it's understandable. Committed to memory. Okay. He took a camera and committed that to his memory. So you can just run this through your mind again, okay? And that is what you should get. Of course, you can also compute this curve more rigorously. And do you want me to do the mathematical version of this? You want to see a mathematical version of this? Okay. Let's see if we can do the mathematical version of this. So what you do then is that if you want to do the mathematical version of this, it's outlined in the textbook. Okay. So f of tau is equal to e minus tau u of tau. H of t minus tau is equal to e to the minus 2 t minus tau u of t minus tau. Multiply this together, okay, and integrate, so you get y of t is equal to the product of these two, e to the minus tau u of tau, e to the minus 2 t minus tau u of t minus tau d tau. Okay, so you have a unit step function here that is non-zero only when tau is larger than 0. Okay, so if you look at this function, it does not allow tau to be less than 0. The lower limit of integration must be 0. Look at this function here. Tau cannot be larger than t. If tau is larger than t, then this is equal to 0. Okay, so the upper limit must be t. So just as what we saw here, when we do the overlap integral, we integrate from 0 to t. Okay, and it's mathematically expressed in this manner. And once you've done this, then you can actually throw out the unit step function because they have been accounted for. Okay, I throw out the unit step function, and now I can integrate. I can take out the term that does not depend on tau, put it on the outside, and then I just have 1 plus 2, right? This is minus 2. Minus, minus, plus, plus, minus. So I have this to integrate. Okay? And what do I get when I integrate this? So I get 2t, but this is just e to the minus plus tau, right? This 1 minus 2 is negative 1, and when I integrate this, I get e to the plus tau when I integrate once. So I will get e to the plus tau evaluated at 0 and t, right? So if I look at this now, it's e to the minus 2t, e to the t minus e to the 0, right? So then it is equal to e to the minus t minus e to the minus 2t. Okay? And this is only non-zero when t is larger than 0. So I should augment the answer with the fact that this is only valid for t larger than 0. Because when t is less than 0, I can obviously see that the integral is 0. Okay? When t is less than 0, there's nothing to integrate when you go to the unit step function. When t is larger than 0, you have to go through this process. So you have to augment the answer with that u of t, unit step function. Okay? Now if you plot the two exponential functions, if you plot the two exponential functions, e to the minus t minus e to the minus 2t times the unit step function, well, you see what you get. When t equals 0, what is that equal to? When t equals to 0, you have 1 minus 1, you have 0. Okay? What happens when t is very small? Of course, if you plot this, you get this. Okay, you get this. Okay, but I argue that it should be linear in t. Let me see if I was correct. What happens if t is very small? How do I approximate this function when t is very small? Remember the Taylor series expansion for an exponential function?
Oh, yeah.
Did anybody commit to memory? What about those students who score 100%? What about Yasher? You score 100% on the first test. What is this when t is very small? What? Okay, it's roughly 1 minus t. Okay, I tell you the answer. E to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x4 over 4 factorial plus. Okay, so if you remember this formula,
So you committed a team.
well, I probably have used this hundreds of times. Okay, so then that is equal to that, and then e to the minus 2t is 1 minus 2t. So if I substitute in, so when t is very small, okay, when t is very small, then at 1 minus t minus 1 plus 2t, u of t. So I would get something like t u of t when t is very small. Okay, so it in fact is correct. It's linear in t. Okay, it's linear in t with the approximate argument that I gave. Okay? So if you do it mathematically, you will get this answer. If you do it graphically, you will get the other answer. But it's usually good to do a sanity check. Okay, a sanity check. Because when you do a lot of mathematics, you tend to make mistakes. And you do not know if you have made the mistake or not. You get an answer, and you do not know if this answer makes sense. If you want to check if this answer makes sense, you do a sanity check by graphical solution. Okay? And then you can pictorially see things. You see how things should look like when you convolve two functions. Okay? So let's do another example. So are there any questions on this? Let's Titus, you have a question?
So how do you get rid of the u tau?
How do I get rid of the unit step function? Well, because I argue that within this range of integration, initially the range of integration was minus infinity to infinity. That is the general definition of what a convolution integral is. But then I say with the unit step function in place, the first unit step function says that the first integral cannot be smaller than 0. The first limit cannot be smaller than 0. So I set this to 0. The upper limit cannot be larger than t. Okay, because this will make it 0, and this will make the other one 0. So I say this should be t. I set the two limits to 0 and t. But then within this range, this is always 1, this is always 1. Okay, since this is always 1, this is always 1, I can get rid of it. I can replace it just with 1. I can go from this step to that step. Then if I go from here to here, then I can do the simple mathematics that I can do. I can go through this step and get this answer. Okay? This is a very good question, okay? Are there any other questions before we move on? So duck soup, right? So let's do the second example then. Say f of tau looks something like this. And this is 1. Okay? And then h of tau looks something like this. This is having a value of 2, and this is between 5 and 6. You also convolve these two functions. Of course, the textbook expresses in terms of tau.